Okay, any questions about that? Yes? Mm-hmm.
That condition is only satisfied in certain areas of the function. In those areas, does the function have the properties?
Okay, so your question is, if I have that property m sub y equals n sub x only in a certain domain, in a certain part of a plane, for some values of x and y, can I conclude these things? And that it's a gradient field in that part of the plane and conservative and so on. So the answer for now is in general no. And when we spend a bit more time on it, actually maybe I should move that up. Maybe we'll talk about it then, later this week instead of when I planned. But so there's a notion of what it means for a region to be without holes. And basically, if you have that kind of property in a region that doesn't have any holes inside it, then things will work. The problem comes from your vector field satisfying this criterion in a region that has a hole in it. Because then what you don't know is whether your potential is actually well-defined and takes the same value when you move all around the hole. It might come back to take a different value. If you look carefully and think hard about the example on the problem set, that's exactly what happens there. Anyway, again, I will say more about that later. But so for now, we basically need our function to be. So I should still say, if you have this property for a vector field that's not quite defined everywhere, you're more than welcome. You should probably still try to look for a potential using the methods that we'll see, but something might go wrong later. You might end up with a potential that's not well defined. Okay, let's do another example. So let's say that I give you this vector field. And the question is, so this A here is a number. The question is, for which value of A is this going to be possibly a gradient? So if you have, your flashcards, then that's a good time to use them to vote, assuming that the number is small enough to be made with. Okay, so let's try to think about it. So we want to call this guy M, we want to call that guy N, and we want to test M sub y versus N sub x. Okay, I don't see anyone. Oh, yeah. Okay, I see people doing it with their hands, and that works very well. Well, okay. So the question is, for which value of A is this a gradient? Yeah, okay, so I see various people with the correct answer. And yes, okay. That's a strange answer on the, but yeah, I see. Okay, that's a good answer. Okay, so the vote seems to be for A equals 8. And let's see, well, if I take M sub y, that is going to be just AX. And N sub x, that is 8x, so I would like A equals 8. By the way, so when you set these two equal to each other, they really have to be equal everywhere, right? So you don't want to somehow solve for x or anything like that. You just want these expressions in terms of x and y to be the same quantities. You can't say, well, if x equals 0, they're always equal. Yeah, that's true, but that's not what we're asking. Okay. So now we come to the next stage of, the next logical question. Let's say that we've passed the test. So we've put A equals 8 in here. So now it should be a potential. Sorry, it should be a gradient field. The question is, how do we find the potential? Okay, so that becomes 8 from now on. question is, how do we find the function which has this as gradient? So one option is to try to guess. And actually, quite often, you will succeed that way. But that's not a valid method on next week's test. So we're going to see two different systematic methods. And you should be using one of these because, well, guessing doesn't always work. And actually, you know, I can come up with examples where if you try to guess, you will surely fail. I can come up with trick ones, but I don't want to put that on the test, but still. So, okay, so the next stage is finding the potential. And let me just emphasize, we can only do that if, you know, step one was successful. If we don't have, you know, if we have a vector field that cannot possibly be a gradient, then we shouldn't try to look for a potential. It's kind of obvious, but it's probably worth pointing out. So there's two methods, and the first method that we'll see is by computing line integrals. So let's see how that works. So let's say that, you know, I take some path that starts at the origin, or actually anywhere you want, but let's take the origin. That's my favorite point. And let's go to a point with coordinates, say, x1, y1. Okay, and let's take my favorite curve, and let's compute the line integral of that field along, you know, the work done along the curve. Well, by the fundamental theorem, that should be equal to the value of the potential at the endpoint minus the value at the origin. Okay. Well, so that means I can actually write f of x1, y1 equals, bless you, equals that line integral plus the value at the origin, and that's just, you know, a constant. We don't know what it is, and actually we can choose what it is, because if you have a potential, you know, say that you have some potential function, and let's say that you add 1 to it, it's still a potential function. Adding 1 doesn't change the gradient. You can even add 18 or any number that you want.